So today we are here to talk about layer caching in OpenResty. So thank you for having me. So a bit about me. My name is Thibault. I work for Kong Inc., the company that made Kong, the API gateway. Also OpenResty contributor on my part-time, and you can find me on GitHub and Twitter talking about OpenResty and Kong developments and other things that happen in the space. So a couple of years ago, I was thinking, I was wondering if after having to re-implement caching all the time in my OpenResty applications, maybe I was thinking there is a better way, a better possibility for a better caching abstraction in OpenResty. So I was wondering, is this question, could OpenResty get a better caching abstraction? So let's define what type of caching. Okay, so OpenResty has a particular strength in the fact that it is dynamic, right? So it is a program that you can configure at runtime and reconfigure at runtime dynamically. And that's the strength compared to vanilla Nginx, okay? So in this particular case, when I talk about caching, I'm talking about the state in the Lua land. And every application needs to do that at some point. Every OpenResty application will have to fetch some data and store it in Lua for processing. So we can talk about dynamic configuration, if you are configuring a reverse proxy, any sort of dynamic logic, if you want to inject load code at runtime, or any sort of client session, or DNS records, or load balancing, etc. So that's the type of caching that I'm referring to, caching in the Lua VM. So there are a few challenges, right, that come with caching in Lua VM in OpenResty. In particular, those three. First of all, the Lua G virtual machine, as we all know, has some limitations, in the amount of a memory that it can allocate. Most likely, you're going to have a limitation of around 2 gigabytes for if you have the right architecture, but it can be quite challenging. So if you want to have a larger data set to cache, you need to have some LRU mechanism in place. Secondly, we have the Lua sharddict, but the Lua sharddict overcomes the first limitations of the Lua VM, but at the same time, it is not as flexible. So you cannot store a table. I mean, we probably all know this. We have to store scalar values or serialize the values in the Lua shard dictionary, which is somewhat expensive. And finally, we deal with the split Nginx workers. So the forked Nginx worker processes, it's kind of hard to keep them in sync, so that if you want to invalidate some value in your cache, you're going to have some real trouble implementing that logic and making sure that it's resilient. So those are, the main three challenges that I thought a caching abstraction should solve very well and make it very easy for anybody out there to cache values in the Lua land. So let's take a little step back, talk about how where all of this came from, this pain. So in Kong, we have some values to cache in the Lua land. So specifically, Kong does some sort of caching of the request and response payload, but in this particular case, I'm going to talk about caching of the configuration. So request comes in from the client. What Kong does is act on the values of that request, and it needs to retrieve configuration value from the database. So this here is what we want to cache. Whenever Kong gets for example, the routes and the plugins from the database, it can then act on those plugins and then decide where this request should be forwarded to, and what plugins to apply to it. But we don't want every request to come through Kong to have to hit the database. That would be terrible. So here is the caching in Kong specifically, and probably in a lot of your applications out there too. So in 2015, this is what caching used to look like in Kong. Basically, it's called get and set, right? So kind of like get or set. So if we get a value, we try to get a value from the cache, and if it's not in the cache, there is a cache miss, then we go and fetch it from the callback, and whenever we get that value back, we set it. So the next call just hits get. So this is a very naive implementation. Some of you may have noticed, for example, we cannot cache false values, we cannot cache nil values. We don't have any sort of protection in terms of cache stampede. So if a lot of workers and a lot of coroutines hit this call, eventually they can create a dogpile effect on your database and sort of highly increase the throughput, the throughput to your database. So this function caused us a lot of problems. We had a lot of bugs, a lot of angry users or wondering why was Kong so unfriendly to the database. And we also knew that we were hitting a bottleneck in the serialization and deserialization from the SHM on every request. That was very expensive. And we knew we could do better performance, especially with OpenResty. So we tried to look for a library. So I tried to look for a library. There exist a few other alternative libraries for caching. The problem with most of them is they have a lot of unpractical APIs. A lot of them also seem unmaintained. There are a few more than those three. There are other ones, but mostly unmaintained, a lack of flexibility in the API and the way you could deploy and integrate those libraries in your applications. And it would require us to rewrite quite a lot of the code that we had written, because the way that they implemented their caching was different from the get or set with a callback. And we wanted get or set with a callback. And some of them are just plainly opinionated. They only work on top of Redis. But for Kong, we support Postgres, and we also support Cassandra. So third of all, we also support Redis for rate limiting. So we really needed something that was much more flexible than that. We could plug it into any type of I/O, which is what I thought would be the coolest caching library actually, and solve most use cases out there. So after deciding that none of the libraries were going to solve our problem, I decided to try to make my own. So a library that we could use in Kong, lots of flexibility, solving a lot of use cases, and very friendly, and very, very performant. So a few off-the-shelf options offered by OpenResty, like where can you cache data in your OpenResty applications? You already can do some caching and implement some caching on your own, and a lot of you probably have done so already. So we have the Lua VM itself, but like we mentioned, the Lua VM has memory limitations. So the tool to overcome that limitation is the RST LRU cache, which probably all of you already know about. It's least recently used eviction queue algorithm on top of the Lua VM, so that you can store values, but when the values start to get too big, then we evict the least recently used values. Very nice. And third of all, we have the shared dictionary, and the shared dictionary is the share between other workers, so overcome a lot of the limitations that we hit with the Lua VM, and also has the really nice added value of being configurable by memory size instead of by plain item size, and we can talk about this very soon. So my idea was to create layer caching where I could have different layers, and each layer solves the problem that it's supposed to solve at the best. And when we combine all of this together, we could have a very powerful solution. And that solution is called OpenResty mlcache. Mlcache for multi-layer caching. So I really like to think about it as the Swiss Army knife of OpenResty caching. It's very flexible, very powerful, and I can walk you through a lot of examples and a lot of the very nice features that mlcache has. Okay, so first of all, this is the API for mlcache. It's a very simple yet obvious API. It has a CRUD method, get, set, delete, and a couple of interesting one, pick, purge, and update that we will dive into. So a very simple and intuitive API, all developed as a key value store. But the underlying store is not made of just the Lua Sherdict or just a LRU cache. It's a combination of all of them with a lot of features along the way and extremely performant. So how can you deploy it? So the usage is pretty simple. You'd have to create a shared dictionary, give it a size, right? And this value here will be considered the layer 2 cache of the mlcache deployment, sitting under the workers at the shared memory layer. Then I can allocate my mlcache library, my mlcache instance, a new with a namespace here. The namespace will group the mlcache instances together. When they are forked across workers, two mlcache instances belonging to two different workers will be identical if they have the same namespace. Second, the cache SHM here, which is the SHM that we define here, right? And third of all, the options. So mlcache has a lot of options. I'm not going to walk through all of them today, but here I define the size of my LRU queue. As we discussed before, the LRU is allocated in terms of item slots, but the Lua shared dictionary is allocated in terms of memory size. So there are tools with mlcache to help you decide what is the best size that you need for your LRU queue. So we can talk about it very soon. So second, I have TTL and negative TTL values. And this is the first clue to one of the very nice features that mlcache supports, which is negative cache. So mlcache will cache hits, but also negative hits, so that when you know something is not present in the data store, you do not have to make a subsequent request until the neg_ttl expires. So it's a very neat feature to say, I want to cache that something is not there, and for a shorter period of time. Or I want to cache that something is there for a longer period of time, like a record or a database row. This is what mlcache will look like as it's running through your processes. So we have a mlcache instance here, and it is the same one with the same namespace, but it is split between the workers, right? So we have 3 workers that have forked from the master process. So each of them is going to hold their instance of mlcache. The layer 1 cache will be comprised of the LRU, OpenResty LRU instance. So if I were to request a value in mlcache, and the value is not present in the LRU, it's called an L1 miss, right? So a layer 1 cache miss. In that case, the worker will go talk to the layer 2, the Lua shared dictionary. If the value is not present in the Lua shared dictionary in the layer 2, we call that a layer 2 miss. It's again another miss. So at that point, the worker has to decide to invoke the layer 3 and make the IO call, right? We call that the callback, and it is protected by the mutex. So the mutex prevents a dogpile effect. So it's a built-in cache stampede prevention mechanism, very simple to implement with the OpenResty lock, but in this particular case, crucial to the performance and the resiliency of your application. So whichever worker gets the mutex, gets elected for the mutex, will be able to call the callback in a protected mode, and then make the I/O lookup to a database, an API, any sort of query, any sort of I/O that you can think of. Whenever the value comes back from the I/O, eventually, the mlcache instance will cache it into the shared dictionary, into the L2, and then promote it to the L1, and finally return it to the caller. And the workers that were waiting on the callback will be able to retrieve it from the shared dictionary. So the other workers do not have to run the callback. They can just directly read the value stored in the Lua shared dictionary. Neat. Okay. So we talked about the Lua shared dictionary serialization. So first of all, you probably realize that at this point, it is occasional whenever we have a Lua shared dict read and write, because most of the time, for the warm values, the values will be directly in the L1 in the Lua VM. So the worker doesn't have to hit the Lua shared dictionary. But whenever that happens, we need the serialization and the deserialization of the values in the Lua shared dictionary to be very efficient. So for that, I made my own serialization format. So in the layer 2, in the Lua shared dictionary, this is how we serialize values. So the key will be namespace. So the key will be namespaced by the name of the mlcache instance, so that different instances from different processes can have can refer to the same values in the shared dictionary. The key itself will be here, and the values will be divided into sections. So the first section will be the type. So the Lua type can be a number, can be a string, could be a table as well. And that's the other very neat feature of mlcache, is that we can store any sort of any type of Lua values, including tables, with proper serialization. We have the insertion time, the add time. This was before the new SHM API. So the new SHM API will be used to improve the serialization format here. And we have the TTL that we want to store that value for, and finally the value here. And this format actually can be encoded and decoded and be fully JITable. So there is no JSON encoding or JSON decoding at all, right? So that the performance of mlcache is really good. Even when we hit the Lua shared dictionary, we don't want any sort of non-JITable code that sits in our hardcode path. The caching library is critical to the performance of your application. So let's start, keeping track of everything we've covered, all the features. So we have a layered caching architecture where we always hit the most efficient cache, and then if we don't have a hit, then we go to the less efficient cache. So just layered architecture. Second of all, we have a built-in cache stampede prevention. So it can be very tricky, especially for new OpenResty users, to get this right. So mlcache does it for you for free, and you don't have to worry about cache stampede. And third, we have a very efficient design. And this pattern is actually used throughout the entire library, so it's not just a serialization format. The whole library is very JITable for the best performance. Okay, now we're gonna explore more features, but for that we're gonna explore practical examples. So a few examples of how you can use mlcache in your applications. First of all, the most obvious one, database caching. So I'm going to walk you through this code, and you'll see that it makes the way mlcache is designed is actually makes it very easy to implement mlcache in your application. So imagine that you have a fetch function, right? So some function that fetches a value from I/O. You probably already have that today, a value that calls a database, makes a database query or anything. So this value is fetch user here. It's a database query function call. So if I want to invoke this value, every time I will make an I/O call, right? But if I want to drop in mlcache on top of this function, then suddenly I have the built-in layer cache for almost free. The way I do that is by having my mlcache instance and choosing a cache key, okay? So a cache key in this case can be my user ID, okay? So my user ID is a cache key here, and I'm gonna call get. And when get results in a cache miss, then mlcache will invoke the fetch user function. So first argument, cache key. The second options, doesn't matter. And then finally we have the fetch user callback with the ID argument, right? Whenever mlcache detects a miss, so miss L1, miss L2, then we invoke the callback. And the callback will be invoked with the cache stampede protection and etc. Right? So it's a very drop-in caching layer on top of your database I/O. The important thing to note here is that if I have an error, the error return value is the value that you should check for your errors that you are reported, but you should not check for if the first return value is nil or not, because nil in mlcache has a very particular meaning. Here, if user is nil, it means that this returned no row. And this is how we have negative caching. So in this case, I have a user, and in that case, I do not have a user, but the next call to get will not hit the database. It will return nil for negative cache. Okay, so, oh yeah, and importantly, you've noticed that user here is a table. So I was able to cache a table for free with no, not having to implement the whole Lua shared dictionary serialization, etc. So super powerful. So we can add caching of Lua tables plus negative cache as an additional feature. Okay, let's keep going. Second example. Let's do something very neat. DNS records caching. This example is very interesting. So it follows the same model. So we use the OpenResty DNS resolver library that's bundled with OpenResty, and we allocate a new resolver, and we eventually have a resolve function, right? This is like pretty standard. In Kong, we have a resolve function like this, and I know I saw the talk yesterday from Alex also had the same implementation, right? So eventually, when you have a resolve function, you don't want to resolve your DNS record for every co-socket call that you're going to make. So if you drop mlcache on top of OpenResty, the OpenResty resolver, this is what it would look like. The host name will be my cache key. And then the resolve function will be my callback, and the callback argument will just be the host name as well. And whenever I invoke mlcache, if the record is not cached in the memory already, then we invoke the query method from the resolver. And the query method returns the DNS record, right? And the DNS record has a bunch of answers, so you select whichever answer you want, so here one. And eventually, we return the IP, no error, and this is the key to providing DNS records caching. we want to set the TTL of the record as the TTL for the cache, but from the response. So not from the option, but from the response. So the third return value here allows us to provide DNS records caching. And there will be even a few more features that we'll talk about in the future that makes this example even more relevant. It's not just about DNS records caching. With this example, with Kong, we actually implemented auth2 tokens caching, because the TTL of the token will be in the token itself. So this is how we use this feature, storing the TTL from the result in Kong. But I also think like caching DNS records with that is also very neat. Okay, the third example will be how to inject logic in OpenResty with mlcache. So, like I said before, OpenResty is dynamic thanks to Lua, and a very neat feature of Lua being an interpreted language is that you can load code at runtime. Okay, that's some of you probably did it already before. In Kong, we have a serverless plugin that allows you to send Lua chunks, and then Kong loads it and then runs your Lua chunks. But the problem with load string is that it's very expensive and it doesn't JIT. So to overcome this limitation, the trick that we use with mlcache that we provide as a feature is called the L1 serializer. So the L1 serializer is a function that is going to run when a value is promoted from the L2 into the L1. So read from the shared dictionary and then write into the Lua VM. And that's the L1 serializer. So here, same example, I fetch some code from the database when I have a miss, and whenever the code will be loaded into the L1 cache, what we do is we inject this middleware function that actually interprets the code from the row and stores it into a f value, which is a function. And when mlcache returns, I can call f as if it were a valid function. And in this way, I have written very minimal code, and I ensure the best performance for my application, whatever my application is doing. Which in this case, okay, I want to load some code dynamically. So this feature was actually contributed by Cloudflare. So the L1 serializer feature itself. So it was a very interesting use case. So Cloudflare has been users of mlcache for some time already, and needed this feature for what they were doing. So it was a very neat feature, and thank you. Okay, new feature, custom serializers between the different caching layers. Now, let's talk about, we finished cover some examples, practical examples, but let's talk about some of the new, some of the way you can deploy mlcache. It's important to remember this example, a bad example, okay? In this case, this is what's going to happen. I decide as an application developer to use a HTTP request header as my cache key, right? So my request header comes from the client, okay? But then I use the request header as a cache key and I make some database select. The problem with that is if I have a malicious client that is sending a lot of different header values, like different high cardinality header values, for example, like A, B, etc. Eventually, this one client is going to exhaust the amount of cache that I have, right? And it's going to fill my cache with garbage values, like cache nils, eventually, because mlcache stores negative values as well. And we don't want that, because then all the users that need their values cached will then hit the database for caching the value for a short period of time, because then the malicious user will still fill up the cache with negative hits. So to solve that, actually mlcache has different ways of being deployed. And so one of these ways is to split the hit and miss caches. So you can specify in the mlcache options a very neat trick. So you can specify Lua sharded hit and Lua sharded misses. And this way, whenever you have a miss, it will be stored in this shared dictionary. So if the callback returns nil, but if the callback returns a correct value, a value that you care about, that you really want to cache, then it will be stored in the hit shared dictionary. So this is how we use mlcache in Kong. It's very important because a lot of the values that we're going to cache are going to be user input, and we don't want to trust that. Okay? Otherwise, it's like you don't want to cache, you don't want to trust user values anytime. But in this particular case, it's interesting how it's a side effect of trusting user input. So, yeah. If you are going to deploy mlcache in production and you're going to have user input as a cache key, I highly recommend you use this. And then another deployment option is to deploy mlcache in a multi-tenant fashion. So on top of the same Lua shared dictionary, I can allocate different mlcache instances. Like we talked about, mlcache has a namespace. So mlcache A in the worker 0 will be the same as mlcache A in worker 1, and mlcache B will be the same as this mlcache B, but they will share the same shared dictionary, but not the same values. So this feature is very useful when you have the need for adding Lua length caching dynamically, but you don't have control over the shared dictionaries, which for Kong a couple times has been the case. So most likely, OpenResty is going to be used in a private deployment. Probably that's how most of you use it. But if not, if you developed a user-facing application with it, like we did with Kong, like I talked about last year, this is one of the limitations, and mlcache overcomes it. And of course, we can combine those two deployment functions. So we can have multiple mlcache values, all of them relying on different shared dictionary for hits and misses. So it's a very flexible deployment capabilities. Okay. Let's dig some more features. So the next feature is caching validation. So the really hard thing about caching and validating in Nginx Lua is going to be the split workers, as we talked about in the intro. And I'm really happy that with mlcache we found a really nice solution to this problem, and a solution that on top of that actually is pluggable and has a lot of room for improvements, and it is just waiting for work to happen, and when it happens we can highly improve the caching validation performance and friendliness of mlcache very, very easily. So currently, the delete API, just like set as well, any write API can be called if in my Lua code path I call update, right? So I have two workers here, and the first one is going to run some code and eventually at T0 delete this key. And this other worker receives another request, but the other worker has a value in the LRU that is still in the LRU because delete ran in the Lua VM of the first worker, not the second worker. So the second worker needs to call update here at the very beginning of the request flow. And when it does so, it receives an event, like polling based, that tells mlcache this instance, oh, you need to delete this user. So it will actually delete it from the LRU, and then any subsequent call to get will actually invoke the callback again, because here at this point this key doesn't have any value. So it's a polling-based implementation. Most likely the worker 0 also has cache.update as the very first function that it calls when it processes a request. And it must be the very first one because you want to make sure that your state is up to date before you process the request, right? Update actually still has like very nice features like timeout, so that if there are too many events to process, then if you're okay with running with the stale data, you can run with stale data. And as always, it's actually very efficient. It's fully cheatable, and when you don't have any event to process, it will actually just nop and pretty much have like nothing to do. So the only thing that it's going to do is a SHM read. So there are some very nice improvements for that coming up in OpenResty, so we'll talk about it. But like I said, it's a very neat API. It's hard to get it right, and it works out of the box. But with the improvements coming up in OpenResty, it can only get better. Cool. Yeah, cache invalidation with built-in inter-process worker inter-process communication. But like I said, actually, it is already something that you can augment as of today. So the cache invalidation can also work with custom cache invalidation libraries, including low-RST worker events that we use in Kong that I talked about last year as well, and even the new IPC libraries that exist that are instead of can be stream-based instead of message-based IPC. It would be very easy to plug those, and for example in Kong we plug low-RST worker events into mlcache. But mlcache comes with a bundled built-in IPC that is very efficient. Okay, so there are still a couple more features. And this one I'm really excited about. It's also a collaboration with Cloudflare to serve stale data. And I'm very happy to say that mlcache, on top of all the caching and the performance and the built-in mutexes and cache template protections and serialization, also supports serving stale data out of the box. So imagine you have a layer 3 lookup that fails. For example, your database has a timeout, or a database is down, or DNS name server has a timeout. In that case, mlcache will be able to serve the stale value to ensure resiliency in your application out of the box. And the only thing that you have to configure is use a resurrect TTL. And the resurrect TTL will resurrect the value for some more time, for 30 more seconds. And once the 30 seconds are over, we'll actually attempt a refetch of the value. And if it fails again, we store it for 30 more seconds. But if it succeeds, we resurrect the value for good. So stale data serving, really important feature. It's somewhat critical to Kong, but to any OpenResty application out there. Now, I have one more feature that I want to talk about. It's more like a concept that mlcache wants to apply. So we're caching values, and it's essential to the performance of our application. It's great, but what is the next step we can take? And I'm very happy to say that mlcache takes the game to the next level and also provides observability and caching metrics. And this way, once you have caching in place and it performs great, you want to have metrics to know, like, could it perform even better? Try to fine-tune your caching. So mlcache has different ways of providing observability and metrics, and we'll have more in the future. One of those ways is the hit level value returned by the cache get function. When I have a value from the cache, whenever I obtain it, even if it's a miss, I also get a hit level. Each value has a special meaning that is documented, but eventually it means that I hit the level 1 cache, the level 2, the database lookup, or I got a stale value that was served to me. So this value is stale, so I want to make a special decision whether I trust it or not. Or maybe I want to implement a fallback value when my value is stale. And if you keep track of the layer that you got a hit from, eventually you can start, drawing conclusions. So maybe my L1 size is not big enough. So like we talked about, it's very hard to get the L1 right because the L1 will be the number of slots. But with mlcache, I can start, deciding like, is that L1 like large enough for me, or do I need to like increase it, because I seem to have a lot of L2 caches and not a lot of L2 hits and not a lot of L1 hits. Okay, another way is a peak function that allows you to read some value from the cache and gets the amount of time that it has already been cached for. It's a very neat way of like hitting the cache but not messing up with the LRU underneath. And we have more plans to supporting more metrics. So there will be a flags API, like a flags value returned from the get function, and you can run a bit mask against that flag to get like more information about what happened. Like this was a stair that was promoted to L2, or this was this was a stair for the second time, and it has been resurrected twice already, etc. And then we have the new SHM APIs that were introduced yesterday. The TTL and free space will be particularly useful to provide more information, more insight for mlcache. Okay, so we have a pretty complete solution. Lots of features. Most of them are essential to any OpenResty application that does caching, and like we talked about, it's mostly all of them, including like observability features that are really essential and like show like really hopefully can take the library to the next step and provide the best caching implementation. In the wild, actually, mlcache has been used in Kong for about 1.5 years now. It has served us very, very well. We have little complaint about it. It works great. We've had contributions from Cloudflare and also from Kong employees, other than myself. We have a very extensive test suite that runs from OpenResty 1.11 to 1.13, and we keep being tested with new versions, and new versions with new APIs will also be thoroughly tested. We even put a note from my coworker here, Poprox, who really likes mlcache, and it's really exciting to see other developers being excited about it. Poprox has also contributed features to mlcache and bug fixes, and it has made caching in Kong very, very easy. Just it breathes. It's even yesterday I was hacking on Kong and implemented like new features, and just thanks to the caching, like it's just so easy to do and make sure that we have like the best performance for Kong. Okay, so there are like a few more improvements coming up to mlcache. I talked about a lot of them already. We have user flag support for OpenResty LRU cache that's coming up. That will allow the flags API for observability that I talked about. We have the Lua-Shardit read-write lock performance improvement contributed by Poprox as well. That will help with the update method. So the update will become very, very cheap. We have the custom L2 serializer, just like L1 serializer. So currently the values in the Lua-Shardit are encoded and decoded in JSON, which can be expensive. Like if you already know what the format of your table is like, you can like provide a Gitable serializer instead. A Lua lane read-write lock for the Lua for the mutex will be very, very helpful as well, especially in deployment and OpenResty instances with a lot of workers. And we have, the need, I think it's not new, for a native inter-process communication mechanism within OpenResty, which, there are some plans around it. So once we have that, the cache invalidation would be very neat. It's ready to be improved already, so. Okay, now I have time for a few questions, I think.